It's, uh, it's my great pleasure to introduce our today's speaker, Nihar Gargava from EPFL. And Nihar will tell us about some results on lattice packings involving division algebras. Nihar, please.
Yeah, so thank you for inviting me, and it is a pleasure to be able to speak here. So today I'm going to talk about some new results that I've developed, and also some more results that I've developed with the help of a co-author. Still, this work is like I mean, we're still open to suggestions and feedback, and yeah, so if you have any by the end of the talk, please let us know or let me know. So yeah, let's start with a very basic example, right? Suppose we have a finite set of numbers, and the constraint is that each of these numbers is positive, but it's also a multiple of some integer m, a positive integer m. And suppose that the average of all these numbers is strictly less than m. So what can you conclude about the numbers AI? So does anyone want to answer this? This is going to be the only question in the talk, I promise.
Some of them must be zero.
That's right. At least one of them is zero, right? Because if all of them are, if none of them is zero, then they're at least m, and then the average will be pushed to more than m. And this argument, you can sort of generalize it, but the overall picture is the same. So if you have a probability space and if you have a random variable, and the random variable is constrained to only take values in some multiples of m, and it's also non-negative, right? And if the expectation value of this random variable is less than m, then it must vanish at some point in the probability space. Right, and we're going to use in our application X to be a set of lattices. You'll see, it'll be an infinite set of lattices. So now, yeah, so some words about lattice, but I'm sure all of you already know all this. So what is a lattice? In this talk, I'll only mean lattices as subsets of Euclidean spaces, by which I mean a discrete subgroup such that the quotient space has finite induced volume. So here you can see in green the co-volume of the lattice formed by the black points. And what I want to do with this, with such a lattice is I want to arrange balls such that the center is on these lattice points, and no two balls are intersecting, and they're all of the same radii. So when you have such an arrangement, you call it a lattice sphere packing or just a lattice packing. And you have a notion of the packing density of such an arrangement. So what you do is, in picture, what you do is you take this very large ball of red color, and then you like let this ball become very large, and as it becomes large, you calculate the percentage of space occupied by the blue color inside this red color. So as it becomes very large, it will become equal to the percentage of space occupied by the blue color inside this green color. And this is always, as you guessed, it's a fraction between 0 and 1. Okay, so I want to make the balls as large as possible, but if I want them not to intersect, then the radius of the ball can be half of this minimum distance between two lattice points. So in this case, I've denoted it by this orange line on the right, you can see. And since I want to maximize the packing density, I will take only those radii that have are equal to half of this minimum distance. In that case, the packing density is equal to this. So I put R as this m lambda by 2. And you can see that this is independent of scaling. So if I replace lambda by say 3 times lambda, then this will scale by a factor of 3 to the power d. D is the dimension, and this will scale by a factor of 3, but the volume of the ball will scale by a factor of 3 to the power D, and the 3 to the power D goes away. So this is independent of scaling. So without loss of generality, so yeah, my goal is to maximize this scaling independent function of lattices over all lattices. So I can assume I can just work with unit co-volume lattices. That's when this denominator becomes equal to 1. And when I have such a setting, what happens is I'm trying to maximize this quantity. So I take a supremum, and I'm maximizing over all lattices that have unit co-volume. And yeah, I can remove this factor of 2 outside, so I get this 1 by 2 to the power D outside, and then I can do a supremum of only this quantity inside. And what I'm now going to add to this is all the lattices lambda are equal to some SLD or some translate of an element of this group of the standard integer lattice. Yeah, and it's a matter of fact that all the unit co-volume lattices look like this. So so this can be used to define our dimensional constant CD, which is defined as the supremum of the quantity inside. And just to visualize that a bit, so in this case, for the lattice shown here, this orange ball is the volume, except that it is not the most optimal, because you can have this lattice for which the volume of the ball that does not intersect the lattice can be slightly larger, and this corresponds to the hexagonal lattice and also the supremum of the packing density. So putting it together, just to restate it again, what I want is I want the largest ball. I want the volume of the largest ball such that for some unimodular matrix, the lattice, which is the G translate, which is a translate with respect to this unimodular matrix, has only a trivial intersection with the ball. Okay, and the supremum always exists because we're bound by this fact that packing density is always between 0 and 1. But yeah, just remember that, you know, CD is not a constant which is between 0 and 1. It's a constant between 0 and 2 to the power D. This is slightly inaccurate. For D equal to 1, it's actually equal to 2 to the power D anyway. Okay, so what is known about CD? CD is known only for these finitely many values. But we can still hope to give a lower bound or an upper bound on CD, and we can understand its asymptotic growth. In this talk, we will only focus on lower bounds. So here is a table of some famous lower bounds. This is, the first one goes all the way back to Minkowski. The second one is a bit more recent. So this bound the first bound was, the history is it's related to the finiteness of the class number. Anyway, this ball, there was also a work of Rogers in between, which I haven't mentioned. Yeah, there's ball, and then there's Vance, but note that all these asymptotic lower bounds are not valid for all dimensions. So the first two are, although valid for all dimensions, if you look at this third one, it's valid only for multiples of 4. And Venkatesh's 2013 bound is only valid for those numbers that can be written as 2 times Euler phi of k for some k. Yeah, and in fact, Venkatesh, although if it doesn't work in all dimensions, the ones that it works in are, it is the best eventually. That's because the ratio of phi n and n can be made as big as log n basically. So So the last bound is bigger than any linear bound, and therefore it is best in infinitely many dimensions. However, and log n grows very slowly. So the first dimension where it's actually the best is t equal to 960. But this gives us an idea that the sort of dimensions that we're interested in is only, what we're trying to work with are high dimensions, basically. So, so here is like a graph of all the record lattices, which are sort of the best lattices for these dimensions. So for 1 to 8, these bounds are exact. For 24, this is also exact, but the other ones, it's actually not, it's just an explicit construction, which means it gives you a lower bound through actually giving basis of some lattice in R to the power D. If you put that into comparison with, okay, so this is also D equal to 72. Yeah, at this point you start to run out of inspiration, and like for D equal to 100, one of the bounds given in the previous slide would be the best bounds. And although they don't perform well in low dimensions, as you can say, so this is the red points are the bounds of ball, and you see that they're actually really bad for in low dimensions. But the thing is, in high dimensions, these are all the bounds that we have, because it's not clear how to systematically construct lattices in high dimensions. So the purple points that have just appeared, they are due to the work of Vance, and as I said before, they're not valid in all dimensions. They're only valid in dimensions divisible by 4. So this is up to 100. We're comparing the bounds of Ball and Vance. So since we're only going to, since all the good bounds are at least linear, we'll, instead of comparing CD, let's compare CD by D for all these bounds. And since we're going to focus on high dimensions, let's put the logarithmic scale on the dimensions. So you see this is 10, and at a distance of 2, you actually have D equal to 100. Okay, so now Venkatesh, if you put all his, for different values of K, if you plot C2 phi K is greater than or equal to K, you get all these points in pink. And then using some systematic construction or some parameterized examples, you can cherry pick a sequence from these pink points, as I'll show you shortly. So in the new work, by using division algebras, we can expand these class of examples given by Venkatesh, and we can get more lattice examples, and some of them outperform the examples by Venkatesh. However, so for example, this is a sequence of points that Venkatesh cherry picks in his example to get an asymptotic growth of order D log D. And so one of the sequences that I was able to cherry pick has a growth not as good as order of D log D, but it outperforms Venkatesh in all these low dimensions. And in fact, it is the best lower bound in all these dimensions up to 10 to the power 50, which is somewhere over here. Okay, so what is this new result? Let me just state it in the form of a theorem. So it says, if D is a finite dimensional division algebra over Q, and if you have an order inside this division algebra, and you have a finite group inside the multiplicative group of D that's also embedded in this order, but in practice, you can align the order in the group so that this works. It's not such a difficult constraint. Then for a space of dimension which is equal to 2 copies of this D, so you take 2 times the dimension of this division algebra, you get this lower bound in this for this D. which is the size of the group. Okay, and this can recover Venkatesh's result, for which you only have to set D equal to this number field, the cyclotomic extension of N. So a number field is also a field, and a field is a division algebra. So what you have is a finite dimensional division algebra over Q, and you can set this order to be the integer points of this division algebra, so the integer points of the number field. And you can set the finite group to be the cyclic group generated by the roots of unity. And then you get the size of the group is n, and you get the space of the dimension of the space is phi n, and 2 times of that is this number. Okay, so the cherry-picked sequence that Venkatesh constructed was by setting n as product of lots of primes by having this highly composite number, and it gives you an asymptotic growth of order d log log d. The new result provides more freedom to cherry pick sequences. However, as I'll shortly tell you, no such sequence will be able to give an asymptotic result strictly better than order d log log d. However, as I've already demonstrated, there is improvement in individual dimensions, and therefore you still get something out of expanding these class of examples. Yeah, we can choose division algebras instead of cyclotomic fields or just number fields. Okay. So I'll give you a taste of how this works and how Venkatesh's result works. So I go back to this probabilistic method. So what I want to do is I want to show the existence of an element in unimodular matrices such that the origin-centered ball has such that the origin-centered ball with volume of m, if I want to show, suppose CD is greater than or equal to m, I find a volume, I find a ball of volume m, and I show that this ball has non-trivial intersection with at least some lattice. Okay, so this is an optimization problem in the space of all lattices, which is the space of all G translates of Z to the power D as G varies in this group. And that's isomorphic to this quotient space of SLDR over SLDZ. This is a very nice space. So a priori, we have just a bijection of sets, but we can pull back the topology and the measure from SLDR over SLDZ. And SLDR has a topology of a locally compact group. So this is just a Lie group modulo a discrete subgroup, and it is also a homogeneous space. And yeah, SLDR is unimodular, SLDZ is a discrete subgroup, and therefore there is a unique left SLDR invariant measure on SLDR over SLDZ. And this measure, in fact, turns out to be a very special measure because this natural measure gives a bounded total measure on SLDR over SLDZ. So in fact, SLDR over SLDZ is a probability space. And therefore we can, and since this is the space of all unimodular lattices of all, the space of all lattices of co-volume 1, we can talk about random unit co-volume lattices, right? Yeah, I wanted to add something here. SLDR over SLDZ is not compact. This is a very important thing and a very important obstruction. Anyway, for D greater than or equal to 2, I mean, of course, for D equal to 1, it's a point. Okay, so now I'm going to talk about this lattice sum function, which is you take this bounded measurable function with compact support. On the right, you have this demonstration here. F is just the indicator function of a ball. And I've also here on the bottom given the area of this ball, which is equal to the integral of F. Okay. And we have, we can now construct this, the lattice sum function, which is a function on the space of lattices And for each lattice, what it gives me is the number of points that is inside the ball. It sums up all the lattice points on F, but what I really get is the number of points inside the ball. But be careful because I've removed 0, and therefore in this example, although there is 1 point inside the ball, I will get the lattice sum function is equal to 0 for this particular lattice. In fact, this lattice is just a cubical lattice with a slight rotation. Okay, so since we can randomly generate lattices, we can talk about the expected value, and that's what I'm going to do in this small numerical simulation. So let's see. So this is some random lattice, and it gave me the lattice sum function equal to 0. Let's sample another. So far I've sampled 2 lattices, and the lattice sum function has been 0 so far. Okay, it is 0 again. Okay, now I have something non-trivial. I got the lattice sum function equal to 2, although there are actually 3 points, but I'm discounting 0. And so far I've sampled 4 points, and the cumulative sum of all the lattice sums has been 2. And I'm going to run this not for 4 or 5 lattices, but for actually a lot of lattices. So let this experiment run on its own, and let's see what we get. So as you see, it's converging somewhat to the integral. It's not quite there yet, but I mean, there's no way you can get it to be exactly equal to the integral, although it's pretty close. So today is my lucky day. Usually I don't get results that are so close. Okay, anyway, I hope I've convinced you that this is what I'm empirically confirming is that the expectation value of this lattice sum function is going to be equal to the integral of f. This is a fantastic result, very classical by Siegel himself. It's called the Siegel mean value theorem. So what you're doing is you're taking the average of phi f, which is this sum, and you're considering the expectation value, and we can do that because we have the probability measure on SLDR over SLDZ, and on the right we have the usual Lebesgue measure, and if you like average it out over all the lattices, you get just like this integral of f. Okay. Okay. So so as you saw, when f is the indicator function of a ball, in fact, we can, due to symmetry, get that the lattice sum is always going to be in a multiple of 2. That's because we have the symmetry of plus minus 1. If you have a point in V, you also have minus V inside the support of F and non-zero points of the lattice. There's a symmetry of 2, right? So therefore, if f is the indicator function of a ball with volume slightly less than 2, then you can use that integrality gap argument that I mentioned in the beginning of the talk, and you can conclude that there exists some lattice such that it intersects trivially with this ball. Therefore, there is some lattice of unit co-volume that intersects trivially with an origin-centered ball of volume 2 minus epsilon, which means there's a very good lattice packing of packing density at least 2 by 2 to the power d, or in other words, this lattice packing constant is at least 2 for all dimensions d. So by using this result of Siegel, you can at least beat Minkowski, who just said CD is greater than or equal to 1. So we used a symmetry of plus minus 1 for which both the ball and the lattice is invariant, and the Venkatesh result and the new result both exploit this idea, except for more exotic symmetries. So Venkatesh's approach was to work with a symmetry of the cyclic group, but for the new result, the symmetries are bigger and non-commutative. So the idea is to take a nice enough subcollection of, so this is for Venkatesh, but it's also true for the new result. You take a nice enough subcollection, and then you have this, and then you average the same phi f over this subset of lattices. So in that case, the set YD was, you take two copies of the ring of integers of the number field, and then you act on it by all these matrices, which are actually just elements of K tensor R. It's made of elements of K tensor R, and it has a determinant 1. So this is actually the set of real points of some algebraic group, which I can tell you in more detail later. Yeah, so YD, it turns out, is isomorphic to this homogeneous space, which is like a number theoretic analog of the previous space, but instead of playing around with the parameter D, which in that case was the dimension of SL, here we're playing around with the number field that we have. And with this bijection, you can make YD a topological space, and then with a bit of work, you can also show that YD has finite measure, and then you can put the probability measure on YD, and then you can do a very similar argument. So YD can be given the probability measure, but why make such a YD, right? Yeah, so the main reason is that every lattice in YD has this symmetry by the roots of unity. So if I have, so remember our lattice was two copies of this ring of integers, and if I take any point in these two copies, and if I act on these, if I act by these roots of unity in a diagonal manner, then this is fixed. Okay, that's not what I'm saying. Okay, what I'm saying is not only all the lattice points in YD have, not only all the lattices in YD have a symmetry by the roots of unity, these symmetries act transitively on the lattices. So if this lattice point, for example, is transported to the same lattice point by the action of the symmetry group, then you have X and Y is 0. So what this gives me is that for each element of this lattice space, the space of lattices YD, we have invariance under the cyclic group, and the action has full orbits on the non-zero points of the lattice. And if F is the indicator function of an origin-centered ball, then you have that phi f lambda is always a multiple of n. So the lattice sum function will always be either 0 or n or 2n. That's because the ball intersects with these lattices only in orbits, right? The ball is also invariant under the group, and the lattices are also invariant under the group. And therefore, yeah, and why does such a ball exist? That's because you can do some averaging tricks over the group, and that's where you actually need the finiteness of the group. So yeah. So Venkatesh also has an analog of the Ziegel's theorem in his 2013 work. He makes the following argument. He says, if you have this space of lattices YD, and if you average the lattice sum function over phi f, it is again equal to the integral of f. And the right hand side here is the Liebig measure on r to the power d. That makes this two copies of OK of unit covolume, right? Because of course this space kr square is isomorphic to r to the d under some choice of basis. but we want to have OK square to be of unit covolume. And then DG is the unique SL2KR invariant probability measure that I mentioned before. So conclusion is, by setting f as the indicator function of a ball in a suitable quadratic form, we conclude that there exists some lattice such that the lattice sum function on the lattice is 0, and therefore some lattice of unit covolume intersects trivially with an origin-centered ball of volume n minus epsilon. And therefore another conclusion is that in a space of dimension 2 times phi n, we show that this lattice packing constant is at least greater than n. Okay, now on to division algebras. The division algebra case is similar. What you do is you take a finite dimensional division algebra over Q, and this time we're working in, we're taking 2 copies of this. So we're working in d equal to 2 times dimension of t dimensions. And we define, we take the tensor with R again, and then we set YD to be this space, which is the space. So we take this order inside the division algebra, and we take 2 copies of this order, and then we translate it around with this group SL2DR. And then this becomes, and then this space is in bijection with this homogeneous space, which is SL2DR over SL2O. And here SL2DR is a bit, so there are various ways you can define SL2DR with like, with the reduced norm and so on. But I think the favorite definition that I like is it is a measure preserving map. So I want to act it on this space, the 2 copies of this space that we have D tensor R, but I want to act it in a measure preserving fashion so that all the lattices that I generate out of this are of unit covolume, right? And when YD consists of these lattices, then they are invariant under the right multiplication by units and O. So you have this symmetry. And this is actually very nice because if you closely observe, this G is acting on the left, right? Like you have an action like this, and this mu is acting on the right, and therefore you have the symmetry, you know, for every G, this product is again going to be 2 copies of O. So yeah, this is, so you have to be careful that although SL2DR is acting on lattices on the left, the finite group, the analog of the finite group that we have in this case is acting on the right. Otherwise, the 2 actions don't commute, and then you will have not every lattice is invariant under the action. Yeah, and then again, you have this transitivity of the action on the non-zero points. So if mu is not equal to 1, and if you have this action of this diagonal action of mu on the lattice points on the right, then you again have transitivity, which is for non-zero points, they're like each orbit is of maximum size. So again, we have an analog of the Siegel mean value theorem, which says if you are averaging the lattice sum function on this even more restrictive space of lattices, it gives us the integral of f. And then again, you can use the same argument, but this time you have a fixed finite subgroup G0, which does not necessarily have to be the cyclic group of n elements. And you can choose f to be the indicator function of a ball invariant under the right action of G0, which is also possible because G0 is finite. And then you have phi f lambda is always a multiple of the size of G0. And then you can use the integrality gap argument again, and you get the bound C of 2 times the dimension of D is greater than or equal to the size of the group G. Okay, that's very cool. Now what I can do is I can just find groups inside division algebras, and I can start constructing examples of lower bounds, except that I will, yeah, so I can, what I'm trying to say in this slide is I don't need to assume G0 to be strictly a subset of the order O. In fact, I can arrange O as the set of integer linear combinations of the group G0 inside D. And in fact, I can make D smaller by taking the division algebra to be just the space generated by the rational linear combinations of G0. And therefore, in fact, I don't need to, so in fact, what this tells me is as soon as I have one finite group inside some division algebra D, I can get the rest through this tightening argument. So fortunately, there exists a complete classification of such finite groups due to Amit Sur. And this is a picture of Amit Sur, and he is this brilliant Israeli mathematician who created this piece of work in 1955. It says finite subgroups of division rings. That's the title. And if you read the first line in the second paragraph, it says the purpose of the present paper is to determine completely all subgroups of division rings. And although that's what he does in this paper, but the paper is very terse because it is a classification result. And it took me a lot of time to struggle with this paper. And although I'll admit I haven't did all the details because, I mean, yes, you can see in examples in these pictures. But here's a summary of what Amit Sir said. He said, so the following construction is called a cyclic division algebra. What you do is you take a cyclic extension of number fields, and then which means that the Galois group should be cyclic, and you take the generator of the cyclic group, and then there is this element gamma in this base field, which has this property that gamma to the k is not a norm of any element in E unless k is divisible by n. That's what it says. So of course, gamma to the n is the norm of gamma because you are in degree n extension. But what this condition says is essentially that is the only possibility for gamma to be the norm of something, for a power of gamma to be the norm of something in E. And then we consider this all these copies of E. So we take n copies of E, and then we add this formal element with the condition that B to the n is gamma. And then we have this multiplication rule that B commutes in this twisted manner with elements of L, and this sigma is the generator of the cyclic group. And yeah, this is the construction. If gamma does not satisfy the non-norm condition, then this is still an algebra, but it's not necessarily a division algebra. And then there's a theorem which says that this construction is a division algebra if and only if gamma is a non-norm element. This is some standard division algebra theory. And in fact, all the division algebras over Q that we're concerned with are cyclic division algebras. The dimension of D is equal to this number, which is you take the dimension of F, and then N is the index of the division algebra. So it has dimension N square over F, and therefore dimension this over Q. And then you have, and then you have this intermediate construction of cyclic division algebras, which is which is, yeah, there are all these details, but I mean, basically you have these two parameters of coprime numbers. M will give you, yeah, so there are these two parameters, and then there are these three auxiliary numbers that you can generate using these parameters. This number n is going to be important. It's the order of R modulo m. And then with this, we consider the cyclic algebra, which is you take E to be the cyclotomic field of M, of the root of M, mth root of unity, and then you take sigma R to be this order R extension, order R Galois automorphism of the cyclotomic field, and you take F to be the fixed field generated by this, and then you take this tth power of the root of mth root of unity to be this non-norm element. I mean, it's not non-norm element. I mean, you wish for it to be a non-norm element, but it's not always a non-norm element. And then Amitsur had this condition of when this is a non-norm element, and this is a horrible, huge condition, and I'm not going to bother you with going into what this really is. But in my experience, it's just really simple to write a computer program to check this condition. Yeah, to give you an overview, you know, the condition goes like, okay, the following one of the, if both the conditions hold, and each of these condition is, you know, one of the following two conditions holding, and then this last one is also, you know, one of the following must hold. Yeah, it's a big, huge theorem. I have no idea how Amit sir was able to do this. But yeah, so the division algebra contains the following group. This group is an extension of two cyclic groups, one of order M and the other of order N. Yeah, and this N, if I recall you, it's just the order of R mod N. So this group is parameterized by these two integers, M and R. Right, and then this group will always embed in U star MR, but I mean, U star MR is not a division algebra always, but we know when it is a division algebra because of the theorem below. And then you can push a little bit more inside this division algebra when the order of 2 modulo M is odd. And that's when you get this slightly bigger group inside this space. This is a tensor of two algebras over Q, and this algebra is actually just the Hamiltonian quaternions, but the rational ones. And then Amitsur then proves that apart from two more sporadic examples, these are like the only family of examples. So here is an exhaustive list of finite groups that you can fit in division algebras. So you see, you have these two sporadic examples, and then you have these two families. And the first one is like the one you probably guessed already. And the second one is the one that I showed before. With a little bit of work, you can fit a slightly larger group inside this. So what I want you to observe here is that in both of these families, the ratio of the size of the group and the dimension of the division algebra is still like phi m by m, right? So up to a constant. Here the constant is slightly larger, but the ratio is still phi m by m, which means even with this division algebra family of examples, you cannot beat d log d. So because the maximum ratio you can get hinges on how large m can be with respect to phi m, and then you have this number theoretic result of Martin, and then you just cannot push anything more. However, we can leverage the second family, which had this slightly better constant of 6, and then we can get the sequence that I showed you before, which grows at order of d log d 7 to the power 7 by 24. That's because the sequence is made of these numbers, which are products of prime, such that order of 2 mod p is odd. So if order of 2 mod p is odd, then order of 2 mod m is also going to be odd, because m is just a product of all these primes, and then order of 2 mod m is going to be the LCM of order of 2 mod p for all these p. And if each of them is odd, the LCM is odd. So therefore order of 2 mod m is odd. And therefore you can use the classification before, and you can get that C8 of phi m is greater than or equal to 24m for all these numbers, which is better than Venkatesh for these numbers, because he gives C2 phi m is greater than m, but it still does not perform as good as Venkatesh, because we have a worse asymptotic growth. This was the sequence of green points that I showed you before in the chart. Yeah, and then this is also an interesting sequence of examples. If you have like this primordial prime, you have a prime which is of the form 1 plus product of lots of primes. Then you can choose an integer r, which is 1 mod each of these pi, but order of r mod q is the maximal possible. It is equal to q minus 1. And then you can use the classification before by setting m to be this number q times q minus 1, and then you can put r to be that number, and then you get this result. And then if you work a bit with this result, you'll see that asymptotically it approaches order d log log d, and it contains only non-commutative symmetries. However, you do not know if there are infinitely many such primes, and this is a notorious open problem. Such primes are called primordial primes. And if there are infinitely many of those, then you have a sequence that approaches order d log log d with non-commutative symmetries. So in summary, Amitsur's work allows us to conclude that there are no asymptotic improvements possible when we allow some non-commutative symmetries, namely the symmetries of these division algebra, the finite subgroups of division algebras. Yeah, and then there is also this new work about effectiveness with a collaborator. Can you construct such lattices algorithmically? Because what I proved is the existence of these results probabilistically. And the fact is, yes, there exists a finite time algorithm so that you can construct this lattice. You can construct a lattice lambda that has this, that's very close to this lower bound. It's arbitrarily close. And this approach is based on the methods of Philippe Moustrou. And the idea is that you can approximate this expectation value by averaging over a growing family of finitely many lattices. So this is all. Thank you for your attention. And this is my email if you want to give me comments or feedback. This is the number of the archive preprint about the division algebra results. And this is a link to the slides. You can run the numerical simulation of the Siegel mean value theorem yourself. And if you want to know how it works, this is some technical details. And if you have any questions now, I'm all ears.
Thank you, Nihar, for this nice interactive presentation. Okay, are there any comments or questions from the audience? Yeah, I see we have Philippe in the audience also. So some of the people mentioned in your talk. Yeah, so maybe just to start the discussion, I'll ask the traditionally silly question. So the picture is like this, right? So Venkatesh, both Venkatesh and you find these symmetry groups. Well, you inside the division algebras, you said Venkatesh uses a cyclotomic group.
Yeah, he uses like he does not use the division algebra picture. He only works with the number fields, which because yeah.
So I guess my question is this. So do you think the fact that you run into the same asymptotic order, right? So you hit the same n log n order. So do you think this is because there are just not enough symmetries that we know of?
Yeah, that's
or this is some
question.
kind of, or some kind of probabilistic. Okay, this is where the silly part comes in. Or is there some kind of probabilistic phenomenon, right? So you're using Ziegel's mean value theorem. So there is some probability involved. Is there something like iterated logarithm, or is there some probabilistic phenomenon? In other words, where does this come from? From the symmetry?
Yeah, that's a very
probability?
fair question, and I've been. Yeah, I attended a talk of Henry Kuhn, and he said, there is some paper about some using some models of physics. They have this theory of phase transition, and then they predict that this order of d log d has something to do with this intrinsic nature of crystal packing. I don't understand that, but I think like from my mathematics point of view, we're relying on this proving technique of using this probabilistic argument. And what you really experience when you play around with these symmetries, the finite group of symmetries, is that the average of the expectation value of this lattice sum, it's not always convergent. Often you will experience that the average of this lattice sum is just infinite, which means that there are lots of lattices having those symmetries, but a lot of these lattices are bad lattices. And therefore, on average, or even though, some of these lattices might be good lattices, on average, you have like nothing. You have a expectation that is divergent. So yeah, I think that order of d log d phenomena has something to do with the symmetries that we are considering are they fit exactly so that the expectation is also convergent, and so that
right.
So if you fit more symmetries in the small dimension, then you will not get a convergent expectation, and that has like that optimization of symmetries and dimensions gives this order d log t.
Right. So what you're saying maybe is that if only we knew which subset of lattices to integrate, to average over. Right. So if we could restrict the integral and then average only on good lattices, we get a better estimate. Hooray! Somehow we would win. But yeah, that's obviously hard.
Yeah, but yeah, like if we restrict it too much, then like the weight of these bad lattices is too much for the integral to converge. Like somehow you want to get only good lattices, but you get too many bad lattices, right? So on average, you get like a integral that diverges. Although, most probably lattices, in fact, you see this in small dimensions, very good lattices are highly symmetric. But if you try to take all the lattices with those symmetries, then somehow you'll get a lot of bad lattices, and the average does not converge.
Right. So another question I was thinking about. So I must have missed this. So Venkatesh's result applies to this two phi of n, or two phi of d dimensions, or two phi of k rather, right? Do we have a similar restriction? So I must have missed this part. So
yeah. Okay.
So is it also?
Yeah, I mean the restriction is we get C of so we instead, so that phi n is actually the dimension of this number field, right? It's
okay, so for you it comes from the division. Yeah, so it must have been somewhere.
Yeah, for me it comes with the division algebra. This if you put D as the number field, then you get dimension as equal to phi n. So this is like the analog of phi n here.
Mhm. Okay, yeah, I gotcha. Okay, so that's where it is. Is it so? How have you looked at the sequence? So what does it do? How does it compare to phi n? Is it sparser? What does it do?
The sequence of you mean like the set of all groups that fit inside division algebra?
Yeah, well, yeah, whatever good sequences you're coming up with.
Yeah, as I said, you know, in this chart, if we go back to the chart.
Yeah, sorry. Okay. There must be some shortcuts.
Yeah, it's actually not working. Oh wow. Yeah, so as you go back to yeah, so these are like the points of Venkatesh, and these are the new points. So like what you get is like you
get more points.
You get like these, for example, you see this green point here and this green point here. You get like more examples if you just try to run a code which just, you know, takes that theorem of Amitsur, checks the results with all these.
So you get denser sequence, you're saying.
Yeah, you can, Venkatesh, you know, he covers almost all examples that can, it somehow, you know, the most interesting division algebras you can make on number fields as far as this lattice construction is concerned. And although he covers most of the examples, but you still get like a few points that he missed out in these small dimensions. And then, yeah, although there is no systematic way to generate these examples of division algebras that consistently outperform Venkatesh. Okay, it's not that there's no way you can do it. It's just that I haven't been able to do it. But it does seem that, I mean, it's in the end, it's futile because you're not doing anything better than order d log of t. So,
right, it's just, yeah. So maybe you could look at the second order term of the asymptotics or something and then say, yeah, okay.
Yeah, but yeah, I mean, you can always make the argument that, you know, these pink points are a subset of the green points. So we have like, you know, yeah, but the thing with these pink points is the lattice is constructed through the results of Venkatesh have symmetric symmetries, sorry, commutative symmetries.
Right.
And the new points have sort of non-commutative symmetries, which is more exotic, but it's doesn't necessarily do better consistently.
Thank you. So I shouldn't take the floor too much. So any other questions?
Do you know, you were saying you have the recent result about, you know, being able to get to these lattices algorithmically.
That's right. That's right.
Is there something similar for the lattices that would come up through Venkatesh's method?
Yeah, it's actually very similar. It's actually yeah. So it's based a lot on Philippe Moustru's work. He's also here among us. Yeah. So like for Venkatesh, you had number fields, and then using like the algebraic structure of these number fields, you can construct a set of lattices that are sort of equidistributed in this homogeneous space of lattices. And then you see that as this family of lattices, which is although finite at every stage, yeah, it's related to this projection with respect to primes. You can go to residue fields, and then you can you get this finite vector space, and then like subsets of those are codes, and then you can take pre-images of codes to make lattices. And then these lattices, like as the prime goes bigger and bigger, like the finite field becomes bigger and the vector space becomes bigger. So you get more and more lattices.
Mhm.
And then these lattices sort of equidistribute among the space of all lattices. And you can approximate instead of averaging over this continuous space, the average is now over this finite set of lattices. And then this expectation value on those finite set of lattices converges to the expectation value on this continuous space. And and then you can, an expectation, you can say one of these finitely many lattices has like a large enough packing density. So that is the idea. So so instead of when you have like division algebras, you have this giant book of Rayner about maximal orders in division algebras, and you go through all that, and then you see like what are the prime ideas and orders of division algebras, and then what does it project to, and you exploit that algebraic structure and you get these codes, and then again you get lattices out of these codes, and then you average over them. That's the idea. Basically, instead of continuous averages, you want finite averages, and you can then get explicitly a lattice that effectively gives you the lower bound.
Okay, thanks.
Perhaps another stupid question on my part. So thank you very much for this nice talk. So is there something you can do about these gaps, right? I mean, it jumps between things where you have a lower bound. Can you perhaps say, okay, you can construct another lattice from the lattice that you have obtained and say something about the densities between the gaps?
That is a good question. Yeah, I have thought about this and I don't see a way to like bridge these gaps. Yeah, that's because we're packing with respect to balls, and then like having, yeah, like if you just try to, like if you have a sphere and or if you just have a circle and then you try to a disk and then you try to extend it as an ellipsoid, it's not clear like how this, like in this new dimension, how this ellipsoid is going to intersect with the lattice points. Yeah, you run into problems like that. So yeah, in short, like I don't have a good answer, but yeah, it's not clear how to do this.
And not even just to increase the dimension by 1. I mean, to me, if you just think of this hexagonal lattice with the disks, right? Increase the dimension, make balls out of it, and then translate it. And then you obtain the face-centered cubic lattice, basically, right?
Yeah, that's right.
I mean, it seems like at least for dimensions +1.
Yeah, but like you lose out on the packing density somehow.
Yeah,
Like
definitely.
You're doing something naive, like when there is a new dimension in there still.
But it gives you an example, and with an example, you have always a lower bound, right?
Right.
I'm not saying it's the best, right? But you can connect perhaps from point to point. We have the optimal lattice. You go one up, perhaps one down. I don't know. But
yeah, that's yeah. I don't have a clear answer over why that does not work, but
all good.
But
yeah, I don't know. Perhaps for future interests, right? All right. Thank you.
All right, thanks for your questions. Let's go off the record and see if we can get some